And so very desert, as you can see here, it's very brown and deserty. When I was about 8, my family moved to Colorado, which is very beautiful, lots of mountains, basically the exact opposite of Australia. And then when I went to college, university, as we call it in Australia, I went to the University of Colorado at Boulder, big school, great school, greatest school in the world. And then I decided to be a little different and then drive all the way over to the East Coast of the United States. And I went to get my PhD in astronomy at the University of Massachusetts. And it's about 3,000 kilometers between these two. That was the worst drive of my life. And little did I know that I would graduate after whining about driving 3,000 kilometers. And I'd move to the opposite side of the world, which is way more than 3,000 kilometers. You know, it takes about a day to fly here, where I am now a researcher here at ANU, where we are at. Yes?
How many songs did you go through while you're driving?
No songs. I drove with my dad.
Oh.
I drove with my dad and his girlfriend at the time. Okay. So, what it means to be a scientist to me. You know, why am I up here talking about scientists? You know, someone that was born on the opposite end of the world, now I'm in Canberra talking about being a researcher, right? So to me, right, being a scientist isn't about one thing, right? Anyone can do this. And it's all about what it means to you. And to me, the world is a wondrous and a curious place. And those are the two words that latched onto me as a child that I really liked. And so STEM, what we call science, technology, engineering, and math, so to me, it's about solving challenges to discover the world around us. Whether that's, you know, trying to discover things like, you know, create a vaccine for the coronavirus, or trying to, you know, discover how galaxies formed in the middle, in the far reaches of the Big Bang. And so what I do personally is I consider myself what I call a star formation scientist. And every image that I show you in this talk is an actual image taken from the Hubble Space Telescope, which I'll get on about the Hubble Space Telescope in a little bit, because that's what I did my PhD on. And I joke with my everyone that I know that I actually love the Hubble Space Telescope more than my husband, and it might be true. So basically what I do is I investigate how stars form, right? And you can see here in the very center. I know people online, unfortunately, can't see my pointer, and I apologize for that. I investigate how stars form in their interactions with the surrounding gas in the galaxies, and how that interaction occurs as they age. And so we call this we call this the star formation process, right? And so there's going to be some terms up here that some of you might have heard before, some of you might not. Stars, something that we've all heard about. Anyone know what this star cluster is called?
The Pleiades.
Yes, the Pleiades, the Seven Sisters. And then once we have our stars, we have the star formation process of where we go around and around and around. Remember, what I said in the very beginning of the Big Bang, there was only hydrogen and helium. How many of us are made of hydrogen and helium?
All of us.
All of us, but are we made of other things?
Yeah.
Yeah, like what?
DNA, tissues.
How about elements? Oxygen? Does anyone have parents' jewelry?
Wait.
Do you have valuable things? Gold? I love gold. We have all this very stuff. And all these heavy elements, these metals, are built up in this star formation cycle. And so what I do is I really study, for my PhD, I worked on the top 2 slices of this, molecular gas and stars. But now as a researcher at ANU, I really work on these 2 slices, looking at the interaction between stars and what we call ionized gas regions, which we're getting to in a little bit. But before we get into that, we're going to, the universe is a big place. Anyone know how old the universe is?
7 billion years.
7 billion years? It's a little older than that.
It's like something minus slash plus something.
And yes. 18 billion? Yes.
13. I have a question.
Yes.
It's approximately 13.8 billion.
It's just over 13 billion years old. Okay, that's a big number. Okay, literally none of us interact with billions in our lifetimes. Like, we literally have no idea how big a billion is. So what we're going to do is we're going to take the universe and we're going to look at those numbers, and then we're going to scale everything down by a factor of about 10 billion. So get a big number we can't understand. We're going to scale it down by a big number we can't understand to get a number that we can understand. So here we are in Canberra. Actually, so right now we aren't, I've given this talk before up at Mount Stromlo, but we're over here a little bit, and we zoom out, and this is an image of Australia taken with the space shuttle. What space shuttle was it taken with? Atlantis. I believe it was taken with Atlantis. You can see, anyone know where we're at in this image? Are we about here?
No.
No. Here?
No.
Here?
Yeah.
Yeah, we're roughly over there. Okay. Here's another image. This is Earth, right? Again, this is taken with the satellites. Space shuttles can't go this high. Space shuttles are actually very low in the atmosphere, which we'll go into that in a little bit. These are taken with satellites that are about, so the shuttle will orbit at a couple hundred kilometers altitude, and satellites will be about 36,000 kilometers. Very, very high in comparison to this. And you can see that it's nighttime here in Japan, and you can actually see Sydney and Canberra down here. You can see the lights. This is an actual scale image and colors of our planets. We can see our nice sun, and then here we are, Earth, with our little moon. Okay? And we all live in what we call the solar system, right?
Yeah.
Orbiting around the sun. And remember, this is not to scale. The sun, right, is a star, our nearest and most favorite star. It has a diameter of 1.4 million kilometers, and we have a distance of 150 million kilometers from that. Anyone know how big that distance is? Has anyone ever here ran a marathon?
Yeah.
Half marathon is better than I have done.
Yeah.
Okay. Okay. So how long is a marathon?
Too long. Very long.
Yes. Yes. Too long. Yes.
Way too long.
Yeah. Okay. Well, if I ran a marathon, I would never complete it. Okay. If you ran a marathon every day, you started at Earth, and you ran a marathon every day going straight toward the sun, you would have to run a marathon every day for almost 10,000 years. That is how long 100. Do I need to move?
No. Okay.
That is how long 150 million kilometers is. Marathon a day for 10,000 years. So we could never get that distance. Okay, so what we're going to do is we're going to divide all these numbers out, and I'm no longer going to talk about these big numbers because they're too big. And we're going to divide out by about 20 billion. Okay, so now this sun, which has a diameter of 1.4 million kilometers, is now going to have a diameter of about a tennis ball, which is about what, 8 centimeters? And I forgot my tennis ball. I do have a really nice tennis ball. But yeah, we do have that one. And so if the sun is a tennis ball, how far away do we think the Earth is? 7.5 meters. Oh, wow, that was very close. It is about 8 meters away. Size of a grain of sand. How far away is 8 meters from this tennis ball? Yeah. Well, no, 8 meters would be, sorry, I'm from the United States. I'm not used to meters. Maybe about this far away or so, right? So we have a tennis ball there, grain of sand on Earth standing over here, orbiting it. Why does it orbit it? What's keeping it in orbit? Let's see. Yes. Gravity. Gravity is this force that always brings us down or brings us together. We'll do that. That sounds a little happier.
To the center.
Okay, anyone know our next nearest star?
I do.
Yes.
It's all about the nearest stars where that will take.
What's it called?
That will take.
What's it called?
The nearest star.
Oh, it is. Did you read that off my slide?
Right.
It's called Alpha and Proxima Centauri. And these are part of the pointer stars, right? So we have a really nice view of them in the southern hemisphere. We have these pointer stars that point to the Southern Cross. Here we have Alpha and Proxima Centauri. So if we have our sun, right, and they live 4 light years away. So if we go outside tonight and we look at these stars, it took 4 years for those photons to travel to us. And that's the nearest thing to us than our sun. Okay, so if the sun is the size of a tennis ball, and we know that the next nearest star is 4 light years away, how far away do we think those stars are in our scale solar system? Yes, all the way in the back.
Oh, I'd say about 100 kilometers.
100 kilometers? What do you say?
I'm not
You're not sure?
What about 5,000?
is about 4,000 kilometers away. So if we go back to Australia and we're right now here sitting in Canberra with a tennis ball, this makes us almost go to Perth, right? So we have our sun, the size of a tennis ball. We have planets that are the size of the grains of sand a couple meters away. And the next nearest star is almost to Perth.
So the next nearest tennis ball.
And this is also space is full of a lot of empty space.
That's why it's called space.
Yes, that is absolutely why it's called space.
And Russians called it space because, like, you know, when you say that there's space in the back, put something in there.
Has anyone ever heard of comets? In the Oort cloud?
Yes.
In our solar system, how far away is the Oort cloud? Almost to Melbourne, actually past Melbourne, right? There are little grains of specks of dust, the size, right? Specks of dust, little snowballs orbiting around our sun in Canberra, all the way down here, that feel the gravitational pull of our sun. Gravity's quite amazing. So we all live in the Milky Way galaxy. This is an absolutely realistic image of what we believe we look like. And we live what we think about halfway out through the galaxy. And we are just but one galaxy in the universe. And this is a very famous image called the Hubble Ultra Deep Field, taken with the Hubble Space Telescope, which we'll get into in a moment. And everything we see here is a galaxy, except for a couple objects. You see things every once in a while with the little spikes. These are foreground stars in our Milky Way, and they're essentially too bright for the telescope. And so we're getting this saturation effect. So if you take a grain of sand, grain of rice, hold it out at arm's length, the little patch of sky that grain of rice covers is how big this image is. And there are over 10,000 galaxies in this image. So you can imagine, if there are 10,000 galaxies in a little rice-sized patch of sky, how many trillions of galaxies have to exist in the entire world? A lot. And the thing that you'll notice is every galaxy is different. They have different colors, they have different shapes and sizes and structures. I really like the more spiral type galaxies, but there'll be some more blobby type galaxies as well. And they all look like this because of their stars. And because all the light that we see in the nighttime sky, and now these galaxies are all coming from stars. So galaxies that have this huge variety in size and color because of the types of stars that they have. And so we're going to talk a little bit about stars, because our sun, while we all love the sun because we exist because of the sun, it's actually a really boring star in my opinion. And so here we go over some scales. So here we have our inner four planets, Mercury, Venus, Earth, and Mars. Sorry, Mercury, Mars, Earth, and Venus, sized by their scale. And we're going to take Earth, and now we're going to compare it with our outer gas giants, the Earth, Neptune, Uranus, Saturn, and Jupiter. Okay, we're going to take Jupiter now, and we're going to place it down here and compare it with our sun. And so this is our sun, how big it is compared to Jupiter. Wolf 359, this is a little what we call brown dwarf. They're really tiny stars. They basically are super duper cold. We can tell that because they're red. I'll get into that in a moment. And then we can see how our sun compares with stars like Sirius. Has everyone seen the star Sirius?
Yes.
Are you serious about that?
Yeah.
Okay, so then we're going to get Sirius, and we're going to put it here, and we're going to compare it with what we call giant stars, right? Pollux, Arcturus, and Aldebaran. Everyone's called, these are very famous stars in the nighttime sky, but we're not done yet. We aren't done yet. We ready?
Yeah.
Now we're going to get Aldebaran, which is a huge star. I mean, look how big this star is, you know, compared to what the sun would have been, where this is Sirius here. We're going to get Aldebaran, and we're going to compare it with Betelgeuse. Has anyone ever heard of Betelgeuse?
Yes.
Betelgeuse is a cool star. It's probably the next star to go supernova and die. It will be amazing. It will probably happen in about 20,000 years. So unfortunately, we won't be able to see it. So there are, yes, there is. Yes, there is. I couldn't remember if I had that slide. Okay. So now a star's lifetime goes roughly 1 over its mass cubed, which means the bigger it gets, the faster it dies. And it dies fast, the bigger that they get. So if we take our sun here, okay, well, sorry. We're going to first take our little brown dwarf. And this is going to live for about 500 billion years. Does Does anyone remember how old our universe is?
Yes.
How old?
13.
It's about 13. So basically, this star will outlive the universe many, 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 many times over. It'll never die. Our sun will live about 10 billion years. We think we're about halfway through its lifetime. It's about 5 billion years old. We can move to some of these more massive stars where they live about 7 billion years. But then what happens when we start getting the really massive stars is we die super fast. Like Betelgeuse, we think will only live between like 5 to 15 million years. Does anyone know when the dinosaurs went extinct?
Yeah.
When?
About like 1 billion or something years.
Went extinct, so they lived like a couple 100 million years ago, but they went extinct about 65 million years ago. So dinosaurs couldn't have even evolved on if a planet was on a star like Betelgeuse. And so then we'll get these stars, those are very giant, right? Then we get these even more massive giants. And these things will live essentially 1 million years. So they're born, and in the grand scheme of cosmic time, they essentially instantly die. So they're actually a really bad place for life to evolve. So before we go a little bit more, we're going to talk a little bit more. We're going to talk a little bit of science, physics. Physics is good. So I'm here to learn knowledge. And scientists have this thing, what we call the electromagnetic spectrum, because scientists like to make things complicated. But this is basically what we call light. What type of light do we see? What type of light do we see?
Visible.
We see visible, right? We see the rainbow. But there are different types of light as well. And the light, we define it by the distance between a peak, because it's a wave, right? And when there's a big peak, right? These are very low energy. So like radio, anyone ever turn on their car stereo? These are actually being carried on light rays. Kind of amazing. And then you can have microwave, right? These things you can like cook food. It gives off heat. And then we can go all the way over to like, very, very energetic waves, and these are gamma rays. So things that like, give like Hulk from the Avengers, his power is gamma rays. So if we take a little dog, this is actually my little puppy, and we look at it in the visible, this is what we see. And it's cute and adorable, right?
Yeah.
Has anyone ever looked at yourself in an infrared camera?
Yeah.
Yeah?
Yeah.
Yeah? How do
I
you
think I
look?
did.
It looks weird.
Yeah, it looks weird. Yeah?
Oh no, we're gonna
Okay,
make
so
the
if
dog look
we
weird.
take Pebbles and look at him in an infrared camera, this is what we see. Do we think Pebbles is as cute?
He looks more husky.
What infrared does is it's showing us where heat is related. So its eyes and mouth are very warm, it's very bright. And if we would look at his paws or its nose, it'd be darker, so it's more cold. Like if you look at me in infrared, like my fingers and my nose are completely black and it looks super scary. So what happens if your dog is bad and eats your homework? How do you find out if that's true to prove it to your teachers? X-rays. You have to go, and that's where we can go and penetrate things like the skin and to hit the bones, and then you can see like, look, it did eat my math homework, teacher.
And a calculator.
And the calculator, please give me the pencil.
Ruler.
And the ruler, yes.
And a pen.
Yes. Okay, so there are things that we can learn in the universe as well from looking at different types of light, right? So here we have the Andromeda Galaxy. Anyone ever heard of the Andromeda Galaxy? It's the Milky Way's sister galaxy. You can actually see it.
Is it my brother?
It's hard to see in the southern hemisphere. We usually have to go to the northern hemisphere, and we can only see the little bulge in the center, and it just looks like a little fuzzy patch in the sky. But it's much smaller than, say, the has anyone ever seen the LNC and the SNC, the Magellanic Clouds, which you can see down here in the southern hemisphere? Yeah, those are cool. You have to go to pretty dark skies. For you to look out, it'll be about as big as your hand. It'll just look like a cloud. Those are actually galaxies. We'll see an image of those later. This is a much smaller galaxy. I mean, it's a very large galaxy, but in the sky it looks very quiet, very small. Sorry. And if we look at this galaxy in the visible compared with infrared, this is what we see. We're looking at the heat, right? This is where young stars are forming, and so they're basically heating up the gas clouds around them. So it's like looking at dust. Or we could go and look at the ultraviolet, very, very energetic wavelengths. And what we're going to see is if we would put these images on top of each other, which I did not do, the infrared would actually very nicely coincide with the ultraviolet, which is telling us where star formation is happening. And so I'm going to give away the punchline. just so we can remember this. And this is that young stars shine very, very bright in the ultraviolet, very energetic wavelengths. And so what we're going to do is we're going to have this galaxy M61 because astronomers are really bad at naming things. And we're going to zoom into a little patch in it, and we're going to see there's a couple things that we can see. And one is we can see like these dark patches. Yeah, everyone see these?
Mm.
This isn't an absence of stars. This is what we call dust, and it's so dense that light actually can't get through these clouds. And then every once in a while, you're going to see these little bright blue dots. Do we see those?
Yeah.
These are what we call baby stars. They're star clusters. I know, right? And sometimes around the star clusters, we see these little red regions. Does everyone see these?
Yeah.
Okay. Does anyone? This is what's happening is essentially our baby stars shining bright in the ultraviolet. What does ultraviolet light happen when it hits our skin? It sunburns us, right? Same color, right? So essentially baby stars are sunburning and destroying their gas clouds. When we do this through a process called ionization. And I know what you're all thinking. What is ionization? Don't worry, we'll cover that. So if we take our hydrogen atom, right? Singly charged proton, one negatively charged electron orbiting around it. What happens is we're going to hit it with some very energetic light.
Electron.
Energy. Like an ultraviolet photon. It's going to come in, and what's going to happen is it's going to give it enough energy that it will rip away the electron, and it's going to remove it. And so this is what we call ionization, right? The atom is being ionized. So we have these baby stars, right? Destroying their gas clouds, and we call this process ionization. But something that you probably noticed in all of these images that I'm showing you is that stars tend to be formed in groupings. You don't tend to have isolated stars. Sorry, people online. We don't tend to have isolated stars. They're forming groupings. And that's what we call, they're forming families. So star clusters, these form the building blocks of galaxies. And we see this really nice star cluster, R136. And this is actually in the LMC. If we look at this image and we see this really bright patch right here, this is a single star cluster, R136, forming in the LMC. And we can see it, it's actually moving through the galaxy. So you can see it's creating this cavity, the hole that's left in interstellar medium behind it. Okay, so young stars, we already know this, I already told you, they emit strong ultraviolet radiation and they ionize their gas and dust clouds around them. But there's this thing called the Earth's atmosphere, right?
Yeah.
And what does this do?
Ultraviolet.
It blocks like 95% of the ultraviolet. And this is good for us, right? Right? Because, I mean, you still need to wear sunscreen when you go outside. But imagine if no ultraviolet was blocked. So if we want to study these stars, these images, we can't do this from the ground because the atmosphere blocks it all. So we have to go to space to observe the UV. And so this is where we built things like Galaxies, was a telescope, as well as the Hubble Space Telescope, which I mainly talk about because this is all the data I did for my PhD work. And so the Hubble Space Telescope is about the size of a bus. Okay, so it weighs a lot. It's like 11,000 tons, and it orbits at an altitude of about 550 kilometers. Right, so you're actually closer. When the Hubble Space Telescope is above us, we're actually closer to the Hubble Space Telescope than to people that live in Melbourne. Right, they orbits really close because it had to be serviced by the shuttles. It travels at 27,000 kilometers per second.
Good.
And to give us a perspective, has anyone ever flown to Europe or the United States?
Yes.
Yeah, how long did it take?
15 hours.
Long time. At this altitude and velocity, it can orbit Earth in 90 minutes. Imagine being able to get to Europe in 45 minutes. That'd be the dream. But we can't. And the really cool thing is it has no engine, has no fuel. It's powered by a gyroscope. Does everyone know what a gyroscope is? The little toys where you spin them one way and the inner wheel goes the opposite way. And so the gyroscopes, they fit in a shoebox and they weigh about 3 kilos. So we have something that's the size of a bus and 11,000 tons. And these little gyroscope wheels move that are weigh 2 kilos, and it can move the telescope about 90 degrees in 15 minutes. Quite impressive. But there is a downside to going to space and being able to observe individual stars. It's expensive. It's expensive. Damn. And it's easier to build ground-based telescopes. So the question that we have is, okay, if we can get these images and we can say, oh, look, all the young baby stars are going to be located in these patches and these beautiful little red and pink patches, which are very bright in optical wavelengths. Can we just look at these bright pink patches, the ionized gas around them, and try to infer the properties of the baby star clusters inside of them? And then we want to build $10 billion telescopes to go to space. And instead we could build 10 telescopes on Earth for the same price. And so that's what we really want to do, is we want to try to connect those two so we can see if we can study the universe around us without having to build telescopes that go to space and constantly need service. All right, let's see. How long about, I don't even know how long I'm talking. I can still go, right? Okay. All right, so what we're going to do is we're going to look a little bit about the properties of stars around us. So we're going to see if we can do this. And this is what we call, astronomers call, this would be the most sciencey thing we do, but don't worry, it's fun. Called the Hertzsprung-Russell diagram. There's two astronomers, American astronomers, called Hertzsprung and Russell that did this. And so what they did was they took the sun, okay? The sun has 10 to the 36 watts, okay? That's a lot of 100-watt light bulbs, right? Has a temperature of 5,500 Kelvin, 1.4 million kilometers in diameter, 5 billion years, and it's massive, 2 times 10 to the 30 kilograms, okay? All these properties, you don't really want to learn them. Is there a way we can relate them all? And so what we can do is we can go to the local universe, the local stars around us, like say the nearest 20 stars. And we're going to look at those stars and place them up here on the diagram, and this is what we see. And our sun, by definition, we have made this to be a definition to fall smack in the middle. It's a very ordinary star. And this is what we see. And there's going to be several things that we notice here. And one is going to be, does everyone see the really nice diagonal sequence that slices this plot across?
Yeah.
Yeah?
Yeah.
Okay, so what happens, so remember, I forgot to say, sorry, I'll step back. Okay, so our y-axis is brightness, right? So when we go to the ceiling, the top of the y-axis, these are very, very bright things. And faint things, these are still stars, so they'd be very bright, live near the bottom. And temperature is on the x-axis, right? So when things are blue, so we're to the right, we're gonna be very, very hot. And when things are cold or red colors, we'll be to the left. Oh, sorry, you guys are backwards. Cold is to the right, blue is to the left. Okay, yes, so we have this main sequence. This is what we call it, slices through. We have these giant stars that tend to live above the main sequence. Everyone remember, what's an example of a giant star? Betelgeuse, that is a very well example. And then we have things called white dwarfs, which live down underneath the main sequence of the diagram. And so when I talk about these baby star clusters, these things that are very energetic, these are stars that live in the very top left. They're very, very bright, very, very hot stars. And to give us a little bit of perspective, right? Because these are big numbers. It's hard to understand these. Humans, we are about 300 degrees Kelvin. So we shine very bright in the infrared. And we're actually as bright as about a 100-watt light bulb in the infrared. So if you put humans on the diagram, we would be about right over here on the x-axis.
Oh.
And then about 6 meters in the ground. Because we would have to divide 100 by 10 to the 36. So humans make really bad star material unless you're Lady Gaga and she was able to become a star. So, I almost gave away the answers. Okay, so we're gonna look at the main sequence. We're focused here on this. Does anyone notice anything? Yes. Yes, as the temperature increases, the luminosity increases. Yes. Yes. What else?
And the young ones are like moving to there,
more like down and the old ones are like up there?
Well, we're not looking at age yet.
Yeah, and
This isn't telling us anything
and the
about
bigger
age
they
yet.
become, the brighter and hotter they become.
The bigger they become, the brighter and hotter they are, right? So hot stars to the left of the room, they're more luminous, right? They're near the top of the plot. They're bigger. We can see that they're actually physically bigger, and they're also blue in color. We don't have small red stars up here, right? As opposed to stars over here, we can see cold stars, stars that are red. They're less luminous, right? They're at the bottom of the plot. They're smaller. They're actually physically smaller in size, and they're red in color. And so a star's color, right, is critical to identify the star because this tells us about the surface temperature. So when we saw the Hubble Ultra Deep Field in the very beginning of our slide of the presentation, right, the different colors were from the different colors of stars, which tells us of the temperature of the star. So has anyone have an electric burner in their house?
Yeah.
Used to, right? And it glows red, and this glows at about 400 degrees Celsius. Has anyone ever seen a blue flame, like a propane flame? Yes? Anyone know how hot propane flames are?
1,000.
They're a couple thousand degrees, right? So hotter things burn bluer. And this is a little bit of the opposite about what we think hot and cold should be. Because like, you know, when our hands are cold, they turn kind of blue. And when our skin's very hot or we get sunburned, it turns red. But we aren't glowing energy objects like stars are. And so that's just a good thing to keep into consideration. Now, if we go back to our electromagnetic spectrum, remember this is flipped from the version I showed earlier. I apologize for that, right? When we have the red colors down here, we have very low, there's big peaks between our light, low energy, and when we go more to blue, we have high frequency or high energy, and so things are going to be very, very hot. So blue wavelengths are more energetic than red wavelengths, so therefore blue stars are also more energetic than red stars. So we will Am I like going backwards? Yes.
Wow.
All right. Okay. So stars, more massive you are, the hotter you are, the bluer you are. When we live on the main sequence, right? Obviously giants and things, stars like this that deviate. So how does this all help us? How does this help an actual astronomer do research? And so what I do is, as I said, I like the really high energetic massive stars. Those are the really cool stars. So what I do is I say, okay, let's make a star, and then we can see if we can understand the physics inside of that star. And I like really massive stars, so I'm going to show you an example of a star that's 50 times the size of our sun, because why model the sun? Because that's quite boring. And stars are all controlled by what we call hydrostatic equilibrium, right? Yeah? Yeah, adults, do you remember going over this when you were in like, maybe second grade? I knew it. Okay, so basically this is just the inward pull from gravity. Remember what I said earlier, gravity pulls things together. It's an attractive force. But we have the star making light, fusing light inside of it, which pushes things away. And so there's this nice balance between the two. And so what I do is I'll take a computer and I'll say, let's take some molecular gas. Remember in those images of the galaxy where there were the dark regions of the galaxy? I'm going to take a big block of gas that's 50 times the mass of the sun, and I'm going to tell my computer, okay, let's make this become a star. And then we're going to start compressing it. The computer programmer start compressing it. What happens when we compress things? Yes. Yeah, and then what happens? What happens when we compress things? They get denser, and what happens to them? Hotter, right? Because the atoms move around a bunch. And so essentially we're going to compress the gas enough until it reaches sufficient density and sufficient temperature that we start fusing, right? We have two hydrogen atoms in the core, and we can fuse them together to create a helium atom. And then that releases a little bit of energy, which is what powers the sun. Okay, so this is a really small subset of the larger HR diagram. So the main sequence here looks like it's horizontal, even though it's really vertical. And so it's going to live on the main sequence, chugging away. If it was our sun, it would live here for about 10 billion years, right? Forming hydrogen into helium, creating light, and it will eventually reach a point where it uses up all the hydrogen atoms in its core, right? Can't make more hydrogen atoms, they're all gone. And this is when the sun will evolve and become a giant star. And so what's happening here, right? It's keeping the same luminosity, right? And it's just moving to super cold and it grows super fat. When stars are approaching the end of their lifetimes, they get super fat and die. And if we move back, they get bloated and depressed and they start to die. If we go back to our scale solar system, remember we have the tennis ball? And the Earth was a grain of sand 8 meters away. The sun, when it does this, will expand to about 10 meters in size. And when this happens, it'll supernova and die. Anyone ever heard the term supernova?
Yeah.
Yeah, that's stellar death. And so what I do is I'm like, okay, while stars live on the main sequence, let's figure out, so now we have these models, right? These models are the physics. I know exactly everything perfectly in the model. And now we go to observations, like let's look at this nebula here, and we want to say, okay, remember, we don't want to go to space to build telescopes to look at these baby stars. But we can observe these beautiful red ionized gas clouds from the ground. So knowing my computer models, can I observe these stars in their ionized gas regions to understand the physics inside of them? So what we do is we'll take an image like this and we'll measure the amount of energy we had to get to ionize all these hydrogen atoms. And for funsies, I just put up a number, 2.6 times 10 to the 48 photons were needed to ionize this gas cloud. So then I go to my models and I find stars that are about the same color as these stars, right? We want main sequence stars, not giant stars, because we know that these aren't giant stars. And we want to find stars that have also emitted the exact same number of photons to balance out our equation. And so then once we have found that best fitting model, that's how we know everything. When I say everything, we don't only know everything about the central star, but we know things like how old the star is, the mass of the star, its elemental abundances, rotation winds, and all that kind of stuff. So we're approaching the end now. So massive hot blue stars, remember they die super fast. And we're just going to look through some really nice images because I really love looking at these images. And we're going to take the example of this image, the Cartwheel Galaxy. Where are all the recently formed massive blue stars? Yes.
In the middle.
Here?
Around the middle.
In the ring.
And not in the ring, not in the blue ring, the blue ring.
Yeah, in the blue ring. Remember, hot, massive stars are blue. And then where are the more older, wimpier stars that kind of live forever? Yes.
I think they're in the middle.
They're in the middle, right? These are more of the yellow, the white yellow stars. Okay. So now we have completed our star formation cycle, right? We get a molecular gas cloud. We start to condense it. We form stars. Stars, when they're young, they're ionized their surrounding medium. After a couple, depending on their mass, could be million, could be a couple billion years. They will die and then turn into supernova, and that gas, which has been enriched with metals created in the heart of stars, will form back into the galaxy again, and we'll get this nice star formation cycle. All right, so by studying the physics of stars, we can learn about how galaxies form and evolve. We've learned that stars are very energetic, right? And they go and they destroy their gas clouds that they're born from. Low mass stars will live for billions of years. High mass stars will only live for a few millions of years, and they die in stellar deaths. When they're low mass, we call those planetary nebulae. You might have heard that term. And when they're high mass, they die in what we call supernova. And it just is part of the life cycle of star formation. And with that, I will end.